Today's discussion will be on the two major types of waves. First off, waves, regardless of what type they actually end up being, they all generate from initial vibration. We also call this an oscillation. So they get this initial vibration. So think of either plucking a string or moving your hand up and down on the battle ropes, okay? And then what happens is that energy that caused that initial vibration transfers that energy through the particles. Okay, so it's a wave is a transfer energy. So it's basically going from, if you have your hand here, I know that's really good, and then you have your rope, the initial vibration that you caused when you moved your hand up and down, that energy is then transferred through the rope, okay, to the end of the battle rope. So when you do your initial flick up and down, that energy then transfers to the end of the rope. Okay, so that's that transfer of energy. But if you notice, the energy, not the matter, is carried from place to place. So when you use your hand to flick this rope, this end of the rope that initially moved is not the same end of the rope that goes at the end of the wave. Okay, it's the same. This rope does not move itself, or the particles of the rope do not move, but the energy is transferred throughout the rope to the end. Okay, so the particles themselves do not move. It's just that energy is transferred. That's also why when you, like, let's say you look at a duck on waves, okay, so here's the wave, you'll notice that a wave would be going like woo, 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 right? But if you look at the duck that sits on the water, it just moves up, up, and then down. Why? Because the particles of the water are themselves not moved. The duck is not moved. It only goes up and down. It is not transferred. If it was transferred, then the duck here would be moved all the way down here. Okay, and the reason why it is because the law of conservation of energy. Okay, energy can either be created or destroyed. It just can be moved from one place to the other or altered. Okay. All right, so let's look at this one where we're describing the pictures below to reference energy transfer, particles, and the waves. Okay, so the energy transfer starts from here and it goes towards that. So the energy transfer moves from the beginning to the end. The particles themselves, they stay put. Now they might move up and down, but they're not going from one end of the energy till the energy runs out. Okay, and the waves themselves, they move. Okay, so they move left to right. They are the representation of this energy transfer. So you can see the waves, which is the energy transfer, okay, but the particles themselves do not move. All right, there are two major types of waves that we will be focused on in this class. The first one is longitudinal. I always think of like an inchworm, if you want to think of it as that. If you've ever seen like a little worm, you know, they kind of like scrunch up, move, scrunch up, move, scrunch up, move. Okay, so you see the wave. If I focus on that wave, whoop, it moves, right? Okay, it's moving from this way to that way, or if you want, you could think of it as going the other way. Okay, but that is longitudinal. It's like a scrunch up, scrunch back, scrunch, scrap back. Okay, but if you look at the particles themselves, the particles, if I focus on that little particle, is only moving back and forth this much, right? It just moves a tiny bit back and forth, but the wave itself moves all the way from that way to that way. All right, now transverse waves, if you look at the particles, okay, this is the type of wave that I'm sure you're most familiar with. It's like, oh yeah, that's the ocean wave, right? That's what you would think of it as. But if you look at the particles themselves, the wave is moving either left to right or right to left, whichever way you want to do, but the wave is moving this way. But if you focus on one individual particle, what way is it moving? Up and down. So the difference between a transverse and a longitudinal is what is happening to those particles. If it's a longitudinal, the particle, which is this little guy, is moving in the same direction as the wave, or we say it's parallel. If you look at the transverse, if you look at that particle, it is moving perpendicular. So this is perpendicular to the wave direction, and this is parallel. I think I spelled that wrong, but okay, there you go. All right, so the first type of wave that we're going to show is, or talk about, is the transverse wave. And that is where the medium, and what we're talking about is the medium is the particle, travels perpendicular, which means if it moves like up and down to the direction of the wave, which moves side to side. Okay, and that was seen on the image before. Light is the key example of what we're going to study for transverse waves. Okay, so this unit is very much the intro to waves, and then we are gonna break it down and do a light unit. And what way does the light go? It goes as a transverse wave. So light, even though it doesn't look like it's actually even a wave, but it actually moves like this. Okay, so light is the key example, and you absolutely need to memorize that. Okay, of a transverse wave. Okay, the way I can remember transverse is it forms like this S. So if you look at transverse, it has that S. It forms like an S if you kind of look at it, like a snake, right, or an S. All right. The other type was the longitudinal, and that's where the particles moved, or the medium, we can also say particles, move parallel or in the same direction as the wave. Okay. They're also known, just to let you know, as compression or pressure waves, longitudinal. We will always call them longitudinal waves, okay? And then you have this back and forth movement of those particles. How do you measure the wavelength? Because we already talked about how do you measure the wavelength of a transverse wave. Remember, the transverse waves look like this. But how do you measure one when it looks like this, right? So what you do is you base it off of what we call as a compression and a rarefaction. A rarefaction is from the most extended to the most extended. Okay, or that's where the rarefaction is where it's most extended. So that's the rarefaction. The compression is very easy. If you think of the word compress, you're like squishing it, and that's exactly where your compression point is like where it's most squished. So compression is where it's most squished, rarefaction is where it's most stretched, and so what you can do to measure a wavelength is measure from a compression to a compression, or from a rarefaction to a rarefaction. So it's kind of like saying we measure from the trough to the trough, or the crust to crust. This one we are measuring from compression to compression, or rarefaction to rarefaction. All right, so let's label the rarefactions and the compressions. So remember, I always like doing compressions first because that word just rings a bell, right? I'm familiar with it. Rarefaction, not so much. So I'm going to label my compression, which is where it is the most compressed. So that would be A, C, and E in this one. So I'm going to say, hey, those guys are the compressions. And then I'm going to then label the rarefactions, which is where it is spread out the most. Okay, so those would be my rarefactions. Okay, so let's bring back a little bit of earth science. We have talked about in the past years, we've talked about P waves and S waves, okay? P waves, have you already learned, is your primary wave. That is why it is called that, because it is the first wave shown. These actually two types of waves travel in different waves. They actually do the longitudinal and the transverse waves, okay? Oh, by the way, the biggest longitudinal wave that we ever know is not these guys, but longitudinal. The biggest example is sound, okay, which we will be focused on in a different unit. But let's go back to the earthquake waves. All right, so we've got these P waves, which are longitudinal waves. They actually travel in this type of a movement where, once again, the particles are moving in the same direction back and forth as the actual wave itself is moving, whereas F waves are moving in a perpendicular motion compared to the direction that the wave is moving. Okay, so P waves, they're longitudinal. What they can do is they can actually go through solids and liquids. So if you look at this diagram over to your right, what I want you to note is that P waves, they are these guys. P waves can go through solids and liquids, right? They're just bent when they go through a liquid. If you look at S waves, they are S because they are secondary, and that's where you get that S. They are the second waves that are seen. And these are the transverse waves. So how I remember transverse, there's a lot of different ways. Oh, and it can only move through solids. So this is how I remember that S waves. First off, transverse, okay? It's the guy with the S. So what does it look like? An S, all right? Then what happens is that it is the secondary wave, and the only thing it can go through is a solid. So notice we've got secondary, solid. S is like the snake, or it forms an S, and then it's the only one with the S. So that's how I remember all the things with S, because once again, I'm not an earth science person. So it's hard for me to remember these, but this is the way I remember it. I base it off of it having the S, and the longitudinal does not. So I know that it can go only through a solid. It forms that S type of shape, or snake, and it is called the secondary wave. Okay, now if we focus on the right-hand side with this Earth, what we've got is this S wave, and notice which one would the S wave be? Well, first off, this looks like a transverse wave, right? But what you notice is that it can't go through the center, and this is how you can prove that the center of the Earth is not solid, but it is a liquid. Why? Because these S waves can't penetrate through liquids, and it can't go through the center of the Earth, so therefore the center of the Earth must be a liquid. All right, so label the above structure as S and P waves. I personally like to focus on the S because that's the one that I know. And remember, S's can only go through solids. P's can go through then the other guys, so solids and liquids. So which one of these can go through solids, or only through solids? Well, this would be that guy. So this would have the S wave, because notice that it's stopped by that center, which is the liquid. And then this guy is on the right is your P wave. How do we know that? Because it can go through the solid, but it also can go through a liquid, even though during the liquid, if you look at it, it is changed and altered. But that is fine. That's how we know that that is the P wave. All right, the last thing we're going to be talking about is interference. And interference is what happens when two waves actually meet up along the same medium. So this happens a lot in music. If you think of music, this is the key to music. This is how you get your different sounds that you can get. The other thing is that it also does happen when actually you're out in the water and when these waves meet up. Okay, there are two types of things that can happen. They can either get bigger or they can get smaller as opposed when they run into each other. All right, so the first one is called the destructive wave. Even before I go over what a destructive wave is, if I told you that when two waves meet, they can either get bigger or they can get smaller, if you think about the word destructive, what does that seem to you? It should be that it gets smaller. All right, because it's destroying it. And this is when we call them that they are out of phase with each other. So that means that they're not going in the same exact direction. So let's look at a picture of this. Okay, so if we look at these two waves, one wave is going up, one wave is going down. Okay, when you see when they run into each other, okay, here's the first wave, here's the other wave, it's going, the bottom wave is going that way, the top wave is going that way. So when they run into each other, what actually happens is they cancel each other out and you will have no existing wave right there. So what you would see is just a flat old line. Okay, and that's because your positives on this cancel out with your negatives, and so therefore you don't see anything and it's just a flat line. This is known as a destructive. So it's when they are out of phase with each other, meaning one is going up and one is kind of like in the bottom part, right? So one is doing, I guess you'd say, the crust, whereas the other is doing the trough at that time. All right, another one is the other type is constructive. So you've got destructive, which destroys it, and then you've got constructive, which builds it up. Okay, and that's when they are in phase with each other, which means they are going in the same direction, whether they are both in their crest point or whether they are in their trough point when they meet up. Okay, what it does is they actually reinforce each other, which means they build off of each other. So if you look at a constructive wave, notice that they are both in this guy, they are both in their crest phase when they run into each other. And so you have your blue and your red right here. But if you look at the result, what happens? You would see a huge one. So if I look at it down here, I have my A and my B. It literally adds the A height to the B height. You don't need to know that, but you do need to know that it actually gets bigger. And so this is your result. It only lasts for a very short little millisecond as they're overlapping, and then they'll keep going in their same direction because it's the energy that's transferring, not the particles themselves. And so therefore they just keep going their own way. They'll go back to the same height afterwards and keep going in their same direction, as you can see in this third little slide. All right, and then you've got the before the interference where they're both the troughs, exact same thing happens. If you look at it, when they overlap, they just get a huge trough. All right, so let's label below the images as constructive or destructive. So if you look at these waves, notice that they are in sync with each other, which means, or they're in phase with each other, which means that they build off. So this has to be constructive. They are constructing it, right? Whereas this guy, if you look at your peak, the other guy is a trough, so you end up with nothing. So this would be your destructive wave. Destructive. All right, hopefully you have a basic understanding of the two different types of waves, which are transverse and longitudinal. Remember that transverse kind of looks like that S. It is found in light, and then longitudinal is the kind of like the inchworm look, and that is found in sound. Then you also have to know that you have your P and your S waves. Remember, S can go through only solids, P's can go through liquids and solids. And then you've got constructive and destructive parts of when waves overlap. Constructive is they build off and they get bigger. Destructive is they destroy each other and they get, when they're out of phase, and they kind of cancel each other out. All right, have a great day.